Okay, early morning hustle. One sample, mean inference. Okay, so go ahead and read this and highlight what you think is important. Okay. All right, so I'm going and read this. A local coffee chain in Seattle. Okay, gives me some context. Is studying the time customers spend waiting for their morning coffee orders. Okay. So wait time is important. The management randomly selects 85 customers during peak hours. It's kind of ambiguous, but it's 85. Our sample's 85 over a 1 week period. Okay, this little piece is a tad bit ambiguous, but we still know it's 85 individuals. It's ambiguous because it's this particular time frame over 1 week. So is it 10 the first day, 20 the next day? But that's fine. We'll keep on going. Tracking their wait time from order to pickup. Okay, how long does it take for them to get their order? All right, so then the average wait time is 4.8 minutes. Okay, that's the sample mean, with a standard deviation of 1.2 minutes. That is a sample standard deviation. Okay, and the company wants to understand if this differs from the target service time of 4 minutes, because if I'm a business owner, I want to make sure that I am serving my customers on time. So here is my sample mean, again with more details. I guess this was rounded. My apologies. Okay, this is sample standard deviation. Okay, and the sample size is 85. We're going to use this sample standard deviation. Okay, 1.08. Okay, interesting. All right, so that's a summary statistic. All right, so statistics, and then in terms of our actual distribution, our data, this is what I would call the gold boxes are a histogram. Okay, it's a histogram. Okay. However, the red curve gives us the density. That just tells us where our majority of our data lies. Okay. And so this is just a curved or smoothed out histogram. And so I would say this is unimodal because it's one hump. Um, and it's slightly skewed, but I'll potentially say it's symmetric. Okay. Where this blue dotted line represents the mean. It could have been the median, but I decided to provide the mean. Okay, that's the mean. All right. And then on the x-axis is the minute. So it's the mean of the minutes. My apologies. Mean of the minutes of wait time at the coffee shop. All right. So that is the visualization. And then finally to the analysis. Okay. This is my test statistic. This is my degrees of freedom. This is my p-value. Okay. I didn't mention if this is a hypothesis test. Actually, technically, I didn't mention what it is. But the idea is that if it were to be a hypothesis test, this would be my p-value. Okay. Based on that p-value, that's extremely small. So we already automatically know what we're going to do to our null hypothesis. We're going to reject it. Okay. And then it also provides us a 95% confidence interval. And again, our sample mean. So the very first, I guess this is 3 minutes and almost 4 minutes, we spent understanding the question, at least understanding the prompt, and then looking at the SSVA, summary statistics, visualization, and analysis. The next portion of this video, how these videos will work, is that we're going to spend time actually answering some questions. So why don't you all pause the video and answer, I believe, the next 9 questions? Take some time, 9 questions. Okay, so I'm not going to put a pause there, but here it says, why does this research matter in real world terms? So this is an important question because we need to make sure we know why we're doing this, right? Why are we even considering this to be important? So in terms of real world, imagine you're a business owner and you want to satisfy your customers. You want to make sure that they are not waiting 8 minutes or 6 minutes. You want to make sure they're waiting below 4 minutes, okay? Or at least 4 minutes. And so what we'll do is, okay, we would want to determine, okay, make this happen. A business owner, you would want to minimize the time it takes for customers to wait in line to guarantee customer satisfaction. Okay, so that's that. When it comes to what we're measuring, what's the characteristic that we're after? It's their wait time. Okay, it's their wait time. And since their wait time is we're measuring time, we'll describe that as a quantitative variable. That's going to be a quantitative variable. Okay? And that's going to always be the case for one sample means. And I may sometimes say one population mean, but I'm using them interchangeably this year. The actual observational unit, the actual unit of observation, we're measuring wait time on what? On the customer of the local shop. Okay, on the customer, on the local coffee shop. Okay, a customer. I should say a customer. Good. And then, who's our target population? It's going to be all the customers at the local coffee shop, or even coffee shop chain. That's another level of ambiguity. Okay, all the customers that visit the local coffee shop. And the sample is going to be the 85 individuals, right? The 85 customers that during peak hours over a 1 week period. Could there be more information provided regarding the sample? Yes. So ideally, like I mentioned earlier, how many individuals visited on Monday, Tuesday, Wednesday, so on and so forth, as well as is it only at one shop? So there's a level, again, a level of ambiguity that needs to be, at least if you're a consultant, needs to be investigated in terms of this work. And so in terms of this experience, did the customers, did the researcher, did the business owner manipulate any of their customers? I would argue no, they didn't. So we would articulate that this was an observational study because no manipulation was actually done to any of the clients or any of the customers. Okay, so it's an observational study. Okay, so then which statistical technique should we use? Hence the name of this video. It's the one sample mean test. More specifically, I didn't emphasize this, but when I first read this, but the company wants to understand if this differs from their target, okay, of 4 minutes, which is a claim, a hypothesis. So this is going to be one sample mean hypothesis test, okay. We also, I'm gonna add some more detail here, okay. And the reason why how do we know this is because we are provided a claim. But I could still answer this using a confidence interval. You may want to add additional detail. I'm going to say the answer, but how do you suppose we could actually implement a confidence interval to actually answer this question? If you're thinking that if we create a confidence interval and if 4 is a plausible value, then we can say that we're on target based on our data. But if 4 is not within the lower bound and upper bound, then we're not in target. So we could have done it that way. So question 8 for most of our videos, or the last question is always going to be a little bit longer, a little bit more detailed. So take a moment, take a pause in the video, and let's see, and then come back. Okay. All right. So in terms of our statistical findings, okay, including relevant measures, perform either a confidence interval or a hypothesis test based on the information given in the problem. We already automatically know that we should be implementing what? A hypothesis test, okay? So when it comes to hypothesis testing, we should first state the null and alternative hypothesis. So when it comes to hypothesis testing, we assume that the null is always true. Okay, and we have evidence to reject it. So we're going to have the null, and based on our experience in the 251, in terms of symbols, our null is that mu. We use a symbol mu is equal to 4 versus the alternative mu is not equal to 4 because it says differ. In the question, it says differ. So that's what makes it not equal to for the alternative. You could use A. I just use 1 because I prefer 1. Okay. And then in terms of words, the null hypothesis is going to be that the population mean of all customers' wait time that visit the local coffee shop is equal to 4. The alternative hypothesis is that it's not equal to 4. Okay? All right, so the assumptions, there are two assumptions. The data needs to be random, and the observations need to be independent from one another, meaning that two people's wait times cannot have an impact on one another. Okay? So like they're two different orders, assuming. Okay? Observations are independent of one another. But at the end of the day, if you honestly think about this, you really think about it, this is really tough to. I would argue that if someone orders a latte and then after them, someone orders a coffee and they do it in linear order, that person that does the coffee, gets the coffee has to wait a little bit longer because the latte takes longer. So that I would say that the assumption would not be met at a realistic coffee shop. At a realistic coffee shop, that assumption would not be met. Even if they order a latte and a seasonal drink, it may take longer. Okay. But we'll still keep going. I think that's a common question every quarter. Granted that the assumptions have not been met. If they're taking if the sample's taking if you're taking individuals consecutively, should we stop the analysis? But no, you keep going. It's a way for us to think critically about the problem a little bit deeper. In terms of the test statistic, you should have seen this before. This is the actual equation. Okay, the first equation. Okay, the x bar minus mu over s over square root of n. S over square root of n is the standard error. Okay, that measures the variability of the statistic x bar. That's again 251 concepts. That's okay. In terms of its the information that we need, x bar was already given to us, s is given to us, n is given to us, and mu is given to us. Okay, so these are the numbers from our output. And then finally, this is what our test statistic would be, 7.06. So we already saw 7.06 up here. Okay, there should be no surprise here. Okay, that's our test statistic. You're gonna hear me mention this in class, but if our distribution is symmetric and unimodal, if our actual distribution is symmetric and unimodal, which in this case it is. I should highlight the first one. Sorry. It's a z distribution. If our test statistic is beyond 3.5 or negative 3.5, we have extremely small p-value. So just keep that in the back of your mind. I'll mention that a lot in class. And then in terms, if n were to be less than 30, and nothing said about the population distribution, and sigma is not given, we then use a t distribution. Both the t and the z are symmetric and unimodal, so therefore a test statistic beyond 3.5 or negative 3.5 will have an extremely small p-value. Okay, so this is our p-value, and our decision is going to be to reject the null hypothesis, okay? Because it's extremely small. So take a couple moments and write out a summary. This is what I have for my summary. Based on a hypothesis test examining customer wait time at a local coffee shop against a target mean of 4, okay, that's our population mean, mu, we reject the null hypothesis, mu is equal to 4, with extremely strong evidence. We have extremely strong evidence against the null. Okay, this extremely small p-value provides overwhelming evidence, statistical evidence, that the population mean wait time differs significantly from 4 minutes. Suggesting, now this is where it goes back to the business owner, suggesting the business owner should investigate and implement changes to their services since the test statistic is positive. Because the test statistic is positive, right? We know it's x bar minus mu. That means that x bar is greater than our target, okay? Now, if this were to be negative, we're like, oh, we're doing good. Everyone gets a raise. You know, we should be fine. So we're bringing the statistics to the context. So if it was negative, we'd say good job. If it was positive, y'all need to work better. All right, well, that's it for this video. Thank you for watching, and more videos to come. Who's excited? Oh, wow.